today's seminar, we have Myriam from the University of Plymouth and the IODP Cube Science Office. And the presentation is titled Investigating the Role of Lithology and Diagenesis on Rock Magnetic Properties of the Genetically Altered Marine Sediments, a pilot study. So Myriam, you can take over the screen and start your presentation.
Perfect. Thank you very much. Thank you, Claudio, for the introduction, and good morning, afternoon, and evening, everyone. So I'm going to present a pilot study and preliminary work on the role of lithology and diagenesis on hysteresis properties of sediment. So this is a study that I've recently started with Laurel Childress at Texas A&M University. And so I will first start by reminding just a few basics. So we all know that the physical properties of rocks and the magnetic properties of rocks depend on the type of rocks we are investigated in. So the rocks are they fall basically in two groups based on the grain density and magnetic susceptibility properties. So they're igneous rocks, volcanic and plutonic in red, are in the magnetite trend. And the paramagnetic trend here is mostly constituted of sedimentary rocks or mineralized and altered rocks. And the metamorphic rocks that are in blue in these two plots fall in either group. And the difference of the, there is one order of magnetic susceptibility difference between magnetite trend and the paramagnetic trend. So this figure here represent the variations of magnetic susceptibility with the type of rocks. And as you can see here, the magnetic susceptibility of rocks overlap between each other. So it's very complicated to use magnetic susceptibility to distinguish between sedimentary rock from metamorphic rock, for instance. So we know that magnetic susceptibility vary and overlap. So why is it? So we know that the magnetic mineral concentration and the magnetic mineral assemblage vary in rocks. And on top of that, at a later stage, during the rock cycle, diagenetic processes and alteration or weathering can also modify significantly the magnetic mineralogy of a rock. So if we cannot use magnetic susceptibility to distinguish between the different type of rocks, could we use other magnetic parameters to distinguish between lithology, which are no longer pristine? So I put pristine in brackets because in pristine, I mean background or unaltered rocks. And so for that, we are going to look at the magnetic minerals. So we know that they have their own magnetic properties, and for instance, coercivity, and they may greatly differ from one mineral to another. So the question that we would like to elucidate in this study is, could we find characteristic rock magnetic properties value that will give us some indication of alteration and diagenesis for a given lithology. So for that, we need to fulfill three criteria. The first one is the rocks should have an homogenized lithology description. Second, we need a suitable sediment material that present both pristine, unaltered, and diagenetically altered feature for same lithology. And finally, a meaningful, statistically meaningful record of rock magnetic measurement for a given lithology. So these three criteria can be fulfilled by studying sediment from scientific ocean drilling, because they allow a long and continuous sediment material record. And in this project, we will focus mostly on IODP expeditions, done with the greatest resolution, and we use the information in the Lily database. So what is the Lily database? So that's a reference database which link lithology to physical, chemical, and magnetic properties data collected from drill cores of IODP Expedition. So this tremendous and amazing job was published last year in G-Cubed. And so the physical, chemical, and magnetic data are open access and can be downloaded from the IODP LIMS database. And the core description as well can be also found online. And the Lily database combines both information into one file, which associate the physical, chemical, and magnetic data to the sediment lithology. So the sediment lithology here is homogenized to get rid of the core describers subjectivity and simplified as well. So this work is also available online. So you can also find the different data files on Zenodo at this address here. And currently, the Lily database contains over 34 million data from 89 kilometers of core recovered on 42 expeditions conducted between 2009 and 2019 with a Childress resolution. So that comprises the two IODP phases, Integrated Ocean Drilling Program and International Ocean Discovery Program. So this map represents the location of all the expeditions that are in the Lily database. So in this project, we focus on 3 expeditions. IODP Expedition 350 here that is in Bonin Rio Arc offshore Japan. The second data set we used is coming from IODP Expedition 375 sites that are located in the Hikurangi Margin in New Zealand. And finally, we use data from IODP Expedition 334 in the Costa Rica Margin. So the first data set is IODP Expedition 350, and we use data from site U1437 here that is located in the Bonin Rio Arc. And we studied a total of 883 samples from the top to about 1800, that is the bottom of the hole. And the samples were collected mostly in turfous mudstones. The data were published in 4 papers with 2 papers here with dedicated to a specific interval and with a higher sampling resolution. So you will see on the next slide a big pack of data for these intervals. So I present here some hysteresis parameters and some ratios with depth for site U1437. So I'm not going to talk about everything, but I will just mention a couple of things. So first, if you look at the remanent coercivity here on the left, you will notice a progressive decrease of the coercivity. So this decrease of coercivity with depth is related to 2 principal processes: magnetite reduction that happens, and also a shift toward volcanoclastic lithology here at the bottom of the hole. So magnetite reduction is the normal processes where with a finer grain preferentially dissolved and the multi-domain preserved in the sediment. The second interesting feature on this figure is on the right with DGH and the ratio as SRM over magnetic susceptibility. They also show a decrease with depth, and this has been interpreted by a progressive pyritization with a slow conversion of greigite to pyrite. So on top of this progressive diagenesis with depth, this site is also interesting because there are also localized punctuated diagenetic events. So you can see on this figure there are 10 diagenetic events here in purple that were recognized based on fluid anomalies in the pore water and in the headspace analysis. So these fluid anomalies indicate local intervals of renewed or enhanced magnetic mineral diagenesis. So for instance, fluid anomaly 1, 3, 6, and 8 will represent a decrease of in coercivity by preservation, by destruction of single domain or vortex state magnetite, or by dissolution, or greigite by pyritization. And on the opposite side of things, fluid anomalies 2, 4, 5, and 9 will represent intervals with enhanced coercivity. And one other thing as well that has been observed by the authors of the study is that between fluid anomaly 7 and 9, there is possible greigite growth at depth. So the second data set that we used in this study is coming from IODP Expedition 375, and from this site, U1518, that is located on the overriding plate of the Hikurangi subduction zone. So in this study, we analyzed more than 250 samples from the top to the bottom of the hole in fine-grained lithology, mostly silty to clay silt lithologies. And so here I show the main results of the study performed on U1519. So same as before, I'm not going to talk about everything, but based on the rock magnetic properties here, we could define 5 magnetic zones, A, B, C, D, and E. And if you look at the rock, usual magnetic properties that we measure, like NRM and magnetic susceptibility, it's very hard to see these 5 magnetic zones that are identified with hysteresis properties. So when we measured 4 diagrams on samples, so almost all the 4 diagrams measured looked like these ones here, with closed contour lines and a peak coercivity between 60 and 70 millitesla. These 4 diagrams are typical of ophiogenic single domain greigite, and we find it everywhere. So you can see here in the green bar where we find greigite, and it's basically everywhere. And this is associated with gas hydrate, either disseminated in the matrix, in the sediment matrix here in blue, or in big chunk, massive layers of gas hydrate in dark blue here. And finally, the third set that we used in this pilot study comes from 2 sites in Costa Rica, offshore Costa Rica, so U1378 and U1379. So by contrast to the 2 other expeditions where I was a scientist, either shipboard or shore-based, I didn't do any work on this expedition. So I used published data. And so about 100 samples were taken in total for these 2 sites in very fine-grained lithologies. So in this pilot study, we focus on 2 rock magnetic parameters. So I will present here the remanent coercivity. So this is these 3 violins plots represent the BCR values for the different lithology identified in the for the analyzed samples, and with the 3 expeditions here. What we can see is that the remanent coercivity has a wide range of value, basically varying from about 10 to 70 75 millitesla. It could also vary across one lithology. So for instance, if you look at mud samples for Expedition 350 or silt and clay samples from Expedition 375, you can see a wide range of BCR value. And why is this? So that could be a different sediment provenance. So keep in mind that these plots don't consider the age of the sediment. Could be alteration. We've seen that these sites have undergo some diagenetic event, and also the mineralogy itself could be different. So this pilot study focused only on fine-grained sediment, so I will not talk about the coarse-grained lithology or the volcanoclastic lithology. Here, this table shows the BCR, the average BCR value for the different lithology, all expedition included. And we know that the magnetic mineral assemblage in sediment is complex, so that's why we have a wide range of variability of remanent coercivity. We can see here 3 lithology with BCR below 35 millitesla. There are 2 lithologies with high coercivity above 60 millitesla, and then an in-between group with coercivity of 40, 50 millitesla. So what we can also see from this table is that some lithologies are represented by a lot of samples and some by a few. The 2 lithologies with high coercivity correspond to, is constituted exclusively of samples from Expedition 375. And we also have samples from Expedition 375 in this in-between group. So let's see what we can say about these 2 lithologies. So we split by expedition, and we can clearly see from this table that samples from Expedition 375 have higher remanent coercivity. So if we go back to the violin plots and put it in a more visual way, so we can define 3 groups based on the coercivity value. So the first group with a BCR value below 35 millitesla would represent pristine, so still in brackets, background unaltered sediment. The in-between group between 35 millitesla and 60 millitesla will represent samples with mixed features. So either with a pristine background feature or diagenetic feature or both altogether. And finally, group 3 with BCR value above 60 millitesla. They are exclusively greigite bearing sediment. And if we look at the other parameter that we selected for this pilot study, so DGH, so from these 3 plots, you can see that DGH also vary with the lithology, but the variation of this parameter is less compared to the remanent coercivity. For instance, mud, there is a variation, but it's not as huge as for BCR. And but there are things that are totally obvious from this plot, from these 3 plots, is that the DGH index for Expedition 375 is higher than the DGH value for the other lithology from the other expeditions. There is also a huge variation of DGH across one lithology, and also the shape. So for instance, these 2, all of them actually, but here it's more obvious. It looks like there are 2 distinct groups of samples within a lithology with a DGH low, a quite low DGH or a quite high DGH. So if we put that on a table, so we see that there are lithology with a DGH pretty low, below 0.1, and 2 lithologies with high DGH value above 0.2, and then this lithology here with an in-between value. And when we split this by expedition, we see that samples from expedition 375 have higher DGH. So expedition 375 samples are very special. They have higher remanent coercivity, higher DGH, and they contain greigite. So if we put the finding on DGH into a visual way here, so we can define 2 groups. So a group with a DGH below 0.2 that will represent the background sediment, unaltered sediment, with a composition similar to the composition at the time of deposition. And the greigite-bearing samples with a DGH above 0.2. So these preliminary results are interesting, and of course there are further work needed. We need to do to investigate other parameters. So we could say that hysteresis properties, remanent coercivity, and DGH can be used as good indicators of magnetic diagenesis in sediment. There is a wide range of BCR and DGH values for the fine-grained lithologies, with systematic higher values for the greigite-bearing sediment. So that's the case of expedition 375. We could also determine threshold value for this 2 type of sediment lithology. I mean, sediment feature, background, or diagenesis with greigite for these 2 parameters. And we need to do more work. So for instance, what about the fluid-related alteration? So this would be done by investigating the samples from expedition 350, separating the samples in the punctuated diagenetic event to the other samples from the other intervals. Could we be more precise and give a threshold value by lithology? So here I just say background and diagenetic sediment, but we have mud, we have silt. So could we be more precise about this fine-grained lithology? And what can we say about coarser sediment? So sand, sandstone, and carbonate-rich sediment. And could we also use other rock magnetic parameters? So these are all the questions that we will need to investigate in the future. And so we will partly answer this by increasing the data set. So the next set of samples will come from expedition 341 in the Gulf of Alaska here. So why we choose this expedition? So for a few reasons. So there are 2 sites that we'll study, site U1417 here and U1419 here. So these 2 sites are part of an ongoing study on another project regarding the magnetic mineral assemblage in non-steady state condition. So U1417 has no traditional shallow sulfate methane transition zone, but has a deep inverse SMTZ with an upward sulfate input from the bottom. And U1419 here is located in an oxygen depletion zone and has a shallow SMTZ and a traditional catabolic reaction sequence that U1417 doesn't have. And there is also a possibility of disseminated gas hydrate in U1419 that could potentially create a non-steady state condition. So thank you very much for your attention, and I can take any question for now.
Thank you, Myriam, for your very interesting presentation. I'll open the floor to anybody with question. You can raise your hand or type a question in the chat. So you presented variation in magnetic parameter depending on the diagenesis and the presence of greigite. Is there any possibility that for the background data, there's some lithology that have instead a lot of pyritization, so it's lowering some of those parameters rather than being really fresh?
That's a good question. So in 375 samples, of course, there is a pyrite as well associated, but in 350, the pyrite content is not that that important. So there is no, like, we don't see pyrite at naked eye, for instance. So it's I would say that what we have as a background value is probably, like, it's not pristine, like totally unaltered. I think there might be like some like very light process because it starts from the beginning anyway. But I think it's as close as possible. It could be from the time of deposition.
All right, thank you. So we have a free question in the chat by Ukar. If you want to, ask your question by yourself, you can also turn on the microphone. Otherwise, I will read it. Okay, so I will read the first question. Do the fork diagrams presenting typical diagenetic features means magnetized as almost completely solved? Or the diagrams are after the removal of biogenic detrital signal?
For the four diagrams that I show, or
I suppose so.
okay, so the two four diagrams that I showed on the slide are from Greigite, are very typical of Greigite. And these are mostly all the samples that I measured. All the four diagrams that I did were like that. The four diagrams that were not like this were mostly coarse grain magnetite, coarse grain low coercivity mineral. So like vortex state, PSD in general, magnetite. And there was no evidence of biogenic magnetite in the samples.
So the next question is, do you have any idea on the timing of Greigite growth?
So for Expedition 375, we were very young, so there was no polarity reversal. For Expedition 350, the intervals with Greigite were remagnetized intervals, so they were showing polarity different from the polarity of the sediment. So Greigite in that case was also formed recently. So recently, I mean in the last Chrome. That's the only we didn't date the Greigite or whatever. There is no information on age. We only did with polarity, so it was for us young.
So they are also asking, how have you identified any biogenic Greigite signal, or is there any overlap with coercivity of the diagenetic grains?
So there was no central ridge feature at all on all our samples. So if there was biogenic minerals, they were completely hidden in the signal. So yeah, that's something that I cannot say if so we didn't see it. I don't say that there wasn't, but we didn't see it.
So we have another question in the chat from one of Falcon student. They are asking what is more reliable between DJH and BCR to identify gray diagenesis.
So that's a good question. BCR is a good indication, but I think both should be combined. In these 3 expeditions that I show, BCR and DGH were totally, they were very good indicators of gregate-bearing sediments. But I think both would need to be combined. A high BCR value combined with a high DGH would probably will very likely indicate gregate-bearing sediment. High DGH may not, and a high BCR may not by itself. So I think we should combine both. So this is just a pilot study. So they are just very preliminary results. There are many questions. We need to do more detailed, not analysis, but more distinction between, oh, this is a sample with an altered, and this is from this lithology, and then do that like almost individually, sample by sample, and redefine all of that. But I think both should be combined. These are good indicators from this pilot study.
Is there anyone else that have any question? If not, we can end the seminar. I just want to remind you that the next seminar will be in a couple of weeks. And then all of our seminars are recorded and online on our YouTube channel. So we can stop recording and move to the more informal catch-up.